Welcome back, everyone. So for this week's experiment, we'll be performing the synthesis of dibenzyl ketone. So this synthesis is not found in the lab manuals. So instead, we've provided this journal article here for you guys to reference and understand how this synthesis works. So to begin, it's very important that we understand the molecular formula of our starting reagent, the phenylacetic acid, or phenylethanoic acid, as well as the molecular formula for dibenzyl ketone. And I've provided both of these here below. So something important for this reaction is that we need to know that we will need 2 moles of the phenylacetic acid for every 1 mole of dibenzyl ketone that we make. So this is the reaction that you can kind of see in here. So for every 2 moles of the phenylacetic acid and 1 mole of iron, we produce 1 mole of the dibenzyl ketone, as well as 1 mole of hydrogen gas, 1 mole of carbon dioxide, and 1 mole of iron oxide. So normally in this experiment, we want to produce about 1.05 grams of dibenzyl ketone. But we're working around half the scale normally with groups. However, for now, we're just going to make sure that we understand that we need about 1.05 grams of dibenzyl ketone. If you read the article, one of the main issues that's stated is that the authors can only make dibenzyl ketone from phenylethanoic acid in about a 71% yield. So if we were to do the same, and we know that we're going to get about a 71% yield, how much do we actually need to make so that we have a final product of about 1.05 grams of dibenzyl ketone? So the first thing we want to do is figure out what would be our 100%. So we can just easily do this by cross-multiplying. So if 71% is supposed to be 1.05 grams, what is 100%? So if we do the cross-multiplication, we get x times 71%, which equals to 1.05 grams times 100%. And we can rewrite this as x equals 1.05 divided by 0.71. By doing this, we can figure out that the actual mass that we need to have in the end is about 1.48 grams. So how much of our starting materials do we actually need to obtain this amount? So we can start off with our phenylacetic acid. I've written it about the same way. So depending on the amount of grams of the dibenzyl ketone that we want, we just do the same thing. So we multiply it by that 71%. And then we divide it by the molecular weight of dibenzyl ketone so that these cancel out to get the moles of dibenzyl ketone. For every mole of dibenzyl ketone, we need to make 1 mole of dibenzyl ketone, we need 2 moles of our phenylacetic acid. And to get the actual mass of the phenylacetic acid, we multiply it by its molecular weight, so 136.15 grams per grams of phenylacetic acid. So by following all of this, we can see that everything tends to cancel out. Moles of PA, moles of PA, and what we're left with is grams of the phenylacetic acid. So by following this formula, we're able to figure out the exact amount of grams of phenylacetic acid we need for a starting material for a starting mass, or I guess for a final mass of dibenzyl ketone. So let's say we wanted that 1.05. We just input it here, and we just solve for our, I guess basically our x. So just remember that in this these calculations, we included something for every 1 mole of dibenzyl ketone, we need 2 moles of the phenylacetic acid. So we included this 2-to-1 stoichiometry for the reaction. Now what about iron? So it's the same thing. Let's say we want 1.05 grams of dibenzyl ketone. We first need to figure out how many moles this exactly is. So we take our 1.05 grams, divide it by 7.71 to get the true value, the 100%. And then we divide it by the molecular weight, and this will give us the moles of dibenzyl ketone. So for every 1 mole of dibenzyl ketone, we need 1 mole of iron. So luckily this is just 1. And to figure out the mass of the iron that we need to convert it to grams. So we just multiply it by its molecular weight. Canceling out all of our units. So grams of dibenzyl ketone cancels out. Moles of dibenzyl ketone cancels out. Moles of iron cancels out and leaves us with grams of iron. At the end, we also multiply it by 1.1. So this is to include a 10% excess to the reaction. So just remember, if these are our starting materials, if the iron is going to be in excess, that means our limiting reagent will be the phenylacetic acid. But we include this 10% excess because it's recommended by the article. Remember, most metals, especially iron, can be impure and can rust because it combines with oxygen in the air over time. So we include a little bit extra just to make sure that we get the reaction down to completion and try to get as much product as possible. So I'm going to just quickly go over the setup. Normally you would do this in the lab and then have the TA or the instructor see how you would if you performed it right. But what's very important for me to kind of mention is when you go into a lab, it's very important to understand what you're going to be doing in there, as well as any type of setup that you need to perform. So just make sure that whenever you're going to perform an experiment, understand if you need to set up some kind of glassware, how the glassware should be set up. So for this experiment, we will be using very special mercury thermometers that can go all the way up to 400 degrees Celsius. So just these thermometers tend to be quite expensive, so it's very important that you stay careful with them. Also, when you set up glassware, always make sure to grease the joints. That way when we set everything up, we can easily slide in our pieces back and forth. So this is the actual setup that you will see. So here we have a 3-necked round bottom flask, and it is sitting in a basically an incubator. So what will happen is we are going to add our reagents, the iron and the phenylacetic acid, into this middle neck here, and it's going to sit inside our flask, our round bottom flask. We're going to turn up the current, and the current will warm up our incubator, and it'll eventually start to boil our actual sample. So this entire setup is for a distillation. So you can see in the leftmost neck, we have our mercury thermometer. This is the one that can go up to 400 degrees Celsius. And we want it to go high so that we can check how hot the inside of the flask is. The second thermometer is here to show the temperature at the neck of the, I guess not the flask, but the joint, so that we can make sure this area is cool, so that once things begin to boil and the gases go up, they eventually undergo condensation and become a liquid up here in this neck. So we can see that as our reaction boils, our product is able to evaporate, go up this neck, and eventually undergo condensation. And the condensation will be able to come down into this neck and collect in this flask. So here is where we're actually collecting our product, the dibenzyl ketone. Something that's very important for this reaction is we need to keep track of the gases, because the gases will let us know how the reaction is going and when it's completed. Because remember that some of the byproducts for this reaction are this hydrogen gas and this carbon dioxide. And we're going to keep track of both. So what ends up happening is, as we have this reaction, the hydrogen gas and carbon dioxide will also continue up, go into this flask, but they will all continue down through this tubing. So they'll continue to go through this tubing until eventually they reach another flask. They will begin to collect into this flask and then push themselves even further until they hit this water bucket. And you'll see that what ends up happening is, as the reaction goes, this tubing will begin to bubble, and you'll see bubbles kind of appear in the water bucket. So this is to show you that some gas is forming in the reaction. So I highly advise you to make sure to watch Dr. Salvador's video, because he's going to show you exactly what is occurring right here. And something else that he will show that's not on here is an inverted granulated cylinder. And this is how you're going to kind of keep track of the volume of hydrogen gas and carbon dioxide that is produced. So let me just make sure. Yes, so you'll add the phenylacetic acid into the middle of the 3-neck flask, so right here, as well as the iron, and just make sure that when you add it that the neck is clean. You don't want to kind of add grease into the system or into the reaction. So once you would set this up in the lab, you would get the instructor to inspect the setup, and once they give you the A-OK, you would dial a transformer. So not seen here, the transformer is kind of this, would be connected to this wire right here. But you would dial the transformer up to 50% voltage, and this would begin to heat up the heating mantle. So for safety reasons, we usually take the transformer and place it into another hood just to make sure that everything is as safe as possible. So to monitor the reaction, we watch the water bucket as well as the granulated cylinder by observing how much hydrogen gas and carbon dioxide is produced, as well as how much water is displaced in the granulated cylinder. So what I mean by this water displacement in the granulated cylinder, what you would do is you would fill a 100 ml graduated cylinder with water, and you would kind of tilt it in a way that you would basically place your hand over the opening of the cylinder and then turn it upside down, and then submerge the opening into the water. When you let go of your palm, the water should stay at the level. And this is how we can kind of check for the amount of gas that is produced. So you can see this better in Dr. Salvador's video, but what's happening is we will have a cylinder here that's been inverted in a bucket of water. So let's say this is our water. And here is our tube that is producing gases. And the gases will go up into the cylinder. So let's say this is our water level and the gases go up. What will eventually happen is, as gas accumulates, the water will begin to be displaced and go down, while the gases will start to take its place. So if this is the before shot, this would be the after shot, and let's say our new water level is here. So here's our tubing and our gases. So you can see that after some time, gases begin to fill up the graduated cylinder, so this is a very good way for us to measure the amount of gases that are produced. Normally you would have a partner, and so each of you would take turns monitoring the reaction for the hydrogen gases that kind of collect in the cylinder. And to check if the cylinder is full of hydrogen gas, what you would do is you would take it out and light a match close to the opening. Remember that hydrogen is quite flammable, so what'll happen is as the fire gets close to the opening, the hydrogen gas will instantly combust and you'll hear a popping sound. So this is our way of being able to check how much hydrogen gas is in, or if there's hydrogen gas present in the cylinder. You'll know that the hydrogen gas stops once nothing combusts, and then you can be sure that the gas that's coming in is now carbon dioxide. So once carbon dioxide starts coming out, you would inform the instructor so that you could progress to the next stage of the reaction. So how much water do we actually need to displace from the cylinder? We need to consider that the air around us is about 21% oxygen, with the remaining non-flammable gases, such as nitrogen, being about 78%. So how much water do we need to actually put into the graduated cylinder before I guess to get the largest pop? Something to remember is that the amount of water that you displace is the volume of the hydrogen gas that you collect. So it's about a 1-to-1. So for every mole of gas that you add into the cylinder, you're removing 1 mole of water. Or in other words, for every ml of gas that you're adding, you're removing an ml of water. So for us to get the largest pop, usually about a third of the cylinder needs to be filled with this hydrogen gas. So if you're using a 100 ml cylinder, that would mean about 33 mLs need to be hydrogen gas. And the other 66 mLs, which is made up of 21% oxygen, so about 14 mLs of the cylinder will be oxygen. So you can see we're getting about roughly about a 2-to-1 ratio of hydrogen and oxygen. And because remember, the ideal gases have the same volume per mole. And so here is that equation. So for every 1 mole of hydrogen gas, we need half a mole of oxygen gas to get H2O. So how much hydrogen are we actually producing? So if we consider the standard temperature and pressure of an ideal gas is 22.4 liters, we need to be able to calculate the volume of hydrogen produced based on the moles of the phenylacetic acid or iron that we are using. In order to make these calculations, we need to know whether we need to use the moles based off of the phenylacetic acid or the moles based off the iron. So I won't say exactly which one just yet, but try to follow along when we go over the mechanism, and you'll see which one actually, or which reactant is in charge of producing the hydrogen gas. So here is the actual mechanism of the reaction. So the mechanism is based on the idea that when you combine acids and metals, you'll make hydrogen gas and salts. So one example is using palladium and hydrogen sulfide. And when you have this reaction to make palladium sulfate, you'll produce hydrogen gas, and this is the spark that actually makes your car battery blow up. Another one is by combining sodium and water, because remember, water is both an acid and a base, to make sodium hydroxide and hydrogen gas. You can try to balance this, but you can see that we need about, there's 1 mole of hydrogen gas here. So there's 3 hydrogens, 1 oxygen, 1 sodium. You have 1 sodium, 1 oxygen, but 2 hydrogens. So the best way to kind of balance this, I believe, is you need for every 2 moles of water, let's see, 2, 4, 2, 4, 2, 2, yes. So this would be the balance equation. For every 2 sodiums and 2 waters, you'll produce 2 moles of sodium hydroxide and 1 mole of hydrogen gas. So this is just the basic idea of we're using acids and metals to make hydrogen gas. Now, to actually apply it, what's happening for our reaction is we're performing an electron transfer from the metal, which is our iron, to the sigma antibond of the hydroxyl group. So we're basically moving 1 electron over into our group, and we're radicalizing the hydrogen and producing a cationic metal. So the hydrogen radicals are able to combine to form our hydrogen gas, and the oxide is able to combine with the oxidized metal to make a salt. So let's go over that kind of here with the actual reaction. So the metal donates a singular electron into our hydroxyl group. This radical is given to the hydrogen, causing them to split, and we get a radical hydrogen as well as our oxide group. Another radical hydrogen from another reaction, so this has to be performed twice, it comes down to form the hydrogen gas. Meanwhile, our oxide, that is negatively charged, is able to combine with our metal that is positively charged. And what we end up getting is a hydrogen gas plus our new oxide metal. So we can do this with our reactant. So we have 2 moles of our acid and 1 mole of our iron. So if we apply this same theory, what will happen is our iron will donate an electron to this hydroxyl group. This hydrogen will take the radical and leave to combine with another hydrogen to form H2. This hydrogen came from another, acid. So we can actually use this iron to basically add another radical to a different acid. So let's say here is the second one, OH and phenyl. Yeah. So let's say here is the second acid. We have 1 radical here, 1 radical here. So 1 is donated to the left, the other one is donated to the right. This will cause the iron to bind to both of them. Meanwhile, the hydrogens on each are knocked off, and they come together to form hydrogen gas. So this is the product that we receive, where the irons have combined with both of the oxide groups, and here is our byproduct of hydrogen. In the second step of the reaction, we just apply heat or add some kind of Lewis acid or a Lewis base. So we have the iron oxide or the iron dihydroxide, and this induces a tautomerization. So here is the actual tautomerization. You can kind of see that this double bond will come and attack the carbonyl group. The carbonyl, this will break this double bond on the oxygen, as well as this oxygen coming into form the double bond. So we get this very interesting tautomerization, this cyclic, this hexacyclic structure. However, this is incredibly unstable. So what'll happen is this negatively charged oxygen will come back to form a double bond. It'll break this bond, which in turn will break this bond. This hydrogen can come in to basically move this double bond and cause it to form here. And it's kind of complex to read it this way, but we'll see that we'll get 3 different bonds. So what I mean, so let's see if I can describe it thoroughly. So this negative charge will come to form a double bond, and it will break this bond. So this iron comes from here. So that is the iron oxide. Meanwhile, when this iron oxide forms, so once this bond breaks and forms the double bond here, this bond breaks and forms a new double bond here. However, there's this hydrogen here, and it's basically going to move its bond and eventually form it over here to form this new double bond. So here is our carbon dioxide, and what is left is our diphenyl ketone, our dibenzyl ketone. So this should be the dibenzyl ketone. So this is the actual mechanism of our reaction. It's a one-pot reaction, and so it's very simple to use. The alternative is a lot more complicated with a lot more reactions. So here I have about 1, 2, 3, 4, 5, 6 reactions total to form the same product. So we can begin by first performing an esterification, where we have a methoxy group that can come in. The hydroxyl group here can take the hydrogen here to form water, and we get our first product. This product can then react with a methoxy salt. So the salt will come in to remove the hydrogen and basically form an elimination reaction. And we're left with this very interesting reactant. By combining A with B, so here, we can undergo a Claisen condensation. So this means this double bond here is going to come in and attack the carbonyl, and we'll get this fairly large molecule here. Next, we need to remove this methyl group. So we can do this using a saponification reaction. So by using sodium hydroxide or some kind of acid, we come in and we basically remove the methyl group and replace it with an alcohol. The next step is the reverse Diels-Alder reaction, where you can kind of see if we arrange the molecule in a way such as so, we can move some of the electrons around, so we can have the hydrogen form, basically we can form a double bond here, which breaks this bond. No. So we can move the electrons around. We can see that as this arrow comes in, it forms a double bond here, which breaks this bond, which comes and forms a double bond here, which breaks this bond, and it ends up taking this hydrogen. So you can kind of see this bond breaks, comes here, forms this double bond, and then this bond breaks, and we're forming carbon dioxide. So here's the carbon dioxide. So once this bond breaks, it comes, forms this double bond. This immediately becomes hindered and breaks, And with nowhere else left to go, it comes off and steals the hydrogen that was removed in the first step. And so we're left with, with this product. Finally, we just undergo that tautomerization where the hydrogen comes back down, or not down. The double bond comes up to form our double bonded oxygen, and then the hydrogen is removed. And so here is our final product. If the R's were pH, then we would have our dibenzyl ketone. So for us to really make sure that you understand this reaction, you need to see the overall pattern of this reaction. You need to know what parts are being added or eliminated or substituted, as well as which elements are being oxidized or reduced in this reaction. So just keep these in mind when you are trying to understand the mechanism, as it'll help a lot when you're performing the experiment. So let's continue a bit with the procedure. So once all the phenylacetic acid has melted and reacted with the iron, the hydrogen will stop being produced. So how do we know this happens? Well, after we've, used up all the hydrogen, if we light a flame by the opening of that granulated cylinder, we shouldn't have any kind of pop because there shouldn't be anything flammable. Once this happens, we increase the variable transformer from 50 to 100% voltage, and what eventually happens is the carbon dioxide should start evolving. Once you reach this 100% voltage, we would place an aluminum foil tent in front of the reaction without touching it to allow the reaction to heat further. So basically we're kind of covering the flask in aluminum to just make it heat faster or heat better. So now with this high heat, the benzyl ketone should begin to start distilling, and we can eventually start collecting it in that round bottom flask. So just remember to record, you would normally want to record the boiling point range, so when the stuff is boiling. Just to follow along, it's very important that you've watched Dr. Salvador's video, because you'll be able to see if our pure benzyl ketone is a solid or liquid at room temperature. So once the benzyl ketone is stilled, the distillation head temperature will drop, but the pot temperature will rise quickly. So basically, once we've collected our benzyl ketone, the temperature in the round bottom flask that has the iron, the temperature will begin to increase very rapidly. So we'll need to turn off the transformer and lower the heat immediately before the thermometer breaks past that 400 degrees Celsius. So after this point, we've basically collected our product, the dibenzyl ketone. So what's left now is to kind of just clean everything up. So you would make sure to remove the hose from the pan of water or the water trap, and yes, you want to remove the hose first. That way the water won't kind of go up and contaminate the sample. You would then carefully weigh the distillate, and you would try to distribute this information with any lab members that you're working with for their lab reports. Once it's cooled, your TA would clean the 3-neck flask by rinsing it with acetone, because we want to remove the organic residues, and acetone is a very good solvent at doing this. And then by covering the iron oxide with hydrochloric acid to dissolve it and dispose of it. You would then disassemble the entire glass setup and put everything away, and that would be the end of the experiment. So once you collect your product, the next thing you want to do is make sure that you actually have a pure product, or that you actually collected what you were expecting. So the first thing we would do is check it using infrared spectroscopy. So here I have the molecule. So there's three functional groups that we should be able to see easily. So we should be able to see the sp2 hybridized hydrogens on our benzene ring. So remember, this should appear above the 3000 wavelength mark, which we can see here. We should see sp3 hybridized hydrogens that belong to these two carbons here. And these should be below the 3000 mark, which we can kind of see here. Finally, which I think is the most important one, we should see the carbon-oxygen, or the carbonyl stretch. So it's a very, very strong peak around the 1700 wave number, and we can see it very clearly here. So by looking at these three peaks, it's very indicative that we were able to purify our dibenzyl ketone, or the 2-propanone 1,3-diphenyl. Now what about NMR? So because we're looking at the hydrogens of NMR, we know that when we have benzene rings, we expect them to show up around the 7 mark. So here we can see them. But we also have another group of hydrogens here. And because there isn't really any neighboring hydrogens to them, we should expect a singlet, which is this one right here. So using both of these as, I guess, guiding points, we're able to determine that we have indeed purified our dibenzyl ketone.